Okay, we're going to start this third part of chapter 19 talking about oxygen nucleophiles. So we are going to look at water, alcohol, and then this diol here, and how they react with aldehydes and ketones. So I know I said this in the last video, and I want to remind you, these reactions will work with aldehydes and ketones, despite the fact that we're just going to use acetone to discuss them. So first, let's start off with water. We can take an aldehyde or ketone and we can react it with water. Now, typically you're going to need some sort of catalyst. We're going to focus on the acidic. We will also see that this can happen in basic conditions, but I want us to focus on acid because for this reaction, the basic conditions can get confusing later on. So let's talk about hydrate formation. You are going to learn the name of a lot of new functional groups throughout this chapter. There are a lot of new intermediates, and so you need to pay attention, right? So hydrate is a good name to know. The mechanism, and we're gonna do the acidic. That's the one we're gonna concentrate on. The mechanism has a lot of your equilibrium arrows, and we're gonna see later on that a lot of these early reactions in this chapter are reversible. So when I do a mechanism, I'm just going to draw the forward arrow, but you will see they're all equilibrium arrows. The equilibrium does not typically favor the hydrate, so this isn't the most useful reaction, but it is a great place for us to start to get into this type of reactivity, to look at this type of mechanism. So we're going to start off with the acid. So again, I'm gonna skip base catalyzed, and I'm gonna go to acid. Acid catalyzed is right here. What am I doing? We're going to take. So I'm using acetone. They're using formaldehyde. It's fine. Now, something that you should remember from your substitution chapter, water is a weak nucleophile. It is not strong enough to attack on its own. So the first step is going to be that protonation. We're going to make this into a better electrophile so that our weak nucleophile can attack. We don't want too many electrons on oxygen because it's group 2. So we push those electrons out and we make our tetrahedral intermediate. We have our water that we added and we have an OH. The final step is just a deprotonation. Since I used equilibrium arrows in this, I might as well finish up strong. What is going to take that proton? It needs to be something that's present. So you do not have any hydroxide. If you took the H plus from hydronium, you've got water. If you took it from HA, you would have a minus, but you don't have hydroxide. So let's use something that's here. Since your catalyst is likely a strong acid, water is most likely going to be what is doing the heavy lifting for the proton transfers. So we used our acid. Oh goodness, dogs are going crazy. Sorry. You used your acid in the first step. You're going to get it back in the last step. That's why it is acid catalyzed. The acid is not consumed in the reaction. And then we wind up with our hydrate. Now, again, I say again because I'm pretty sure I said this in the last video. Pay attention to the conditions. A strong base cannot exist in an acidic environment. A strong acid cannot exist in a basic environment. I will remind you of this multiple times. Now, a more useful reaction that is similar, but it's going to take a few more steps, is going to be between our alcohol. And so I'm just going to use a general alcohol, but this could be methanol, ethanol, propanol, etc. And we're going to have an acid catalyst again. This could be done in basic conditions, but again, we are going to focus on acidic. The basic conditions with aldehydes and ketones is more complex. Something I want to point out, you are going to use 2 moles of your alcohol, but it is likely also your solvent, so you have excess of this reagent. I will not always put a 2 here. Assume you have enough. If you didn't have enough, you would just get a weird mixture of products. The product is going to be this double ether, these 2 alkoxy groups on the same carbon, and that is known as an acetal. All right, so 2 ethers on the same carbon is your acetal. You also wind up making some water here. It's a small byproduct. You don't have to show that for me. The acids that are useful, sometimes you may see para-toluene sulfonic acid, sulfuric acid. Frequently, it's just brackets and an H+, right? Some sort of acid catalyst. So let's walk through this mechanism together. It's a big one. So I do recommend that you spend some time looking through these. Even though you're not going to have to draw it for me, I may ask you questions about this. For instance, what's the first step? Well, again, we have a weak nucleophile. So our first step is going to be making our electrophile better. We're going to protonate that carbonyl, which is going to make this a much better electrophile, and now our alcohol can attack. We are going to make our tetrahedral intermediate. We have an OH, an ORH. Don't lose protons. And we're going to get our acid back. Now, we use our acid and get it back twice in this mechanism. So I want to think about what is available to me. So you can see here they used HA and then A. If I'm not going to use HA, then I could also just use my alcohol. I'm not going to use water because water is not one of my reagents or my solvent. If anything, we're just generating a very small amount. So the alcohol is what I'm going to reach for. But again, HA or your alcohol, both are fine. This is going to lead us to a neutral intermediate. This is a different functional group. This is called a hemiacetal. Hemiacetals are not particularly stable, and with one big exception we'll talk about later. But it will keep reacting to give us that acetal. So because we're in an acidic environment, and you can take that from HA, you can take it from your protonated alcohol, you can just do H+. We're going to protonate that alcohol. We know we want that OH gone, and OHs are not good leaving groups, especially in acidic conditions. Maybe if it was basic, you could lose OH minus, but not in acidic. But water is a great leaving group. Now, what is important, and people often mess up in this stage, the water doesn't leave behind a carbocation. There are lone pairs on the oxygen here that are going to fold in at the same time. So that's when we lose our water. And we have recreated this positively charged carbonyl, right? Really reactive with our weak nucleophile, the alcohol, of which we have plenty. So we make our tertiary intermediate again. We've got OR, we've got OR, tetrahedral intermediate, I'm sorry. And we've got one last proton that we need to remove. So you use your acid, you get it back. You use your acid, and then finally you get it back. So again, just for consistency, I've been using the alcohol. So I'm going to go ahead and snatch up that proton, and that is going to leave me with my acetal. So in this reaction, obviously there is a lot going on with the mechanism. So you should know the general order of the steps, that you protonate to make a better electrophile. There's an nucleophilic attack. You have a lot of proton transfers, and you have a hemiacetal intermediate. Lots of notes over here from Klein. Another thing that I want to point out, and I'm going to be repetitive about this, you have an aldehyde or ketone reacting with an alcohol and acid. So you want to pay attention to what functional groups are reacting. So we've got just a specific example with formaldehyde and acetone. Breeze, go sit down. Sorry, you get to join me in my living room with my dogs for this lecture. And if any of you were worried, I am protected. Breeze. Come here. Okay. All right, back to oxygen nucleophiles, our mid-lecture break. So the biggest difference is just where the equilibrium lies when it comes to aldehydes versus ketones. I am not going to ask you about that. Assume that it will make the acetal product. I'm not going to trick you there. The last oxygen nucleophile we look at is the diol. So if we use a diol, we can make a cyclic acetal because both of the alcohols are on the same compound. So if we take our aldehyde or ketone, we treat with this this diol and acid, we can make this cyclic acetal. Now, what's great about this is you can remove it and it makes a really wonderful protecting group, which we're going to cover in a little bit. I am not going to go through this mechanism because I just went through it. I would recommend to you to practice that last mechanism with this problem. Right? The only difference is going to come right. Let me use my little pointer here. The only difference is going to come right here, where the second nucleophilic attack occurs. It's just going to come from the other side of this piece. But all of the steps are exactly the same, so this would be a great place for you to practice. Since it can be removed, this is, and do we talk about this here? Yes. We can use this as a protecting group. So you can take an entire class just on protecting groups. So we're just going to look at this one and explore how it can be helpful. What's important is that a protecting group can go on and not be reactive under certain conditions, and then you can easily remove it. So for an aldehyde or a ketone, you can put that cyclic acetal on, and then you can reverse that reaction by just drowning it, right? If we lose water, we have a dehydration. When we make our acetal, hydrating it is going to push that equilibrium in the opposite direction. This is just a Le Chatelier's principle, right? If I add more product, then I'm going to shift the equilibrium back towards reactants. We're going to talk about that mechanism in a future video. But for now, let's just remember that this is reversible. Just add water. All right, so here you want an acid catalyst. Here you want a dilute acid. So how can this be useful to us? Well, when we're dealing with different carbonyl compounds, we may want to be selective. So I'm going to make a version of this problem. I've got an ester and a ketone. So we're going to address this problem momentarily. If I want to reduce both of these, I can use lithium aluminum hydride and water. This was an organic 1 reaction. We will see it a bunch in these 2 chapters, so get comfy with it. Lithium aluminum hydride, you may see it as LiAlH4 or LAH. And it must be a 1-2 step reaction. If you put them together, that's dangerous and you will lose at least some portion of a point. If I treat this reagent if I treat this compound with these reagents, what I will wind up doing is reducing both carbonyls to alcohols. So I have 4 carbons and I reduce the ester to an alcohol and I reduce the ketone to an alcohol. Now I already had some selectivity from organic 1. If I treat this with sodium borohydride and methanol, this is a weaker reducing agent and it only reduces aldehydes and ketones. So it'll leave that ester in place, but it will reduce the ketone. Reduces only aldehydes and ketones. So what they're asking us here is for the opposite trick. Reduce only the ester, leave the ketone in place. Well, we don't have a reducing agent that can do that, but we can protect it. So if I want to only reduce the ester, then the first thing I can do is protect, and I'm going to use my diol and acid. That is going to give me this acetal, but that reaction doesn't occur on esters. Then I can treat with LAH. And for this second workup, and you can show this in separate steps, but I'm going to show it all together. Instead of working it up with just water, I'm just going to add a little acid to that workup. And that is also going to reverse my protecting group. Remember, this was reversible. All I had to do to knock it off was treat with acid and water. And so I will get my ketone back, but I will have reduced the ester. And then that can all be written out as one solution, just using your numbers. Here we go. So you can see there was the protection. We lost water. That's step 1. Then we treat with LAH or LiAlH4, same thing. And that last step, we're going to acidify. That pops the hydrogen on your alcohol and it pops that protecting group off. So now we have all the control here. We can reduce all carbonyls. We can reduce aldehydes and ketones selectively. We can reduce carboxylic acid derivatives selectively. And ultimately, that's what we want, all the control. This is the last thing we're going to talk about with the oxygen nucleophiles, and that is the hemiacetal. So in organic, you're going to learn that they're not stable and they're difficult to isolate. And then you're going to go to biochem and you're going to see them all over the place. And the reason for that, there is one type of hemiacetal that is very stable, and that is the cyclic hemiacetals when you're dealing with carbohydrate chemistry. So when your open chain sugars convert to their cyclic sugars, that cyclic form is a hemiacetal, right? You have a carbon with an OH and an OR group attached, and those are indeed stable. We are not going to look at those, though, in organic any more than just to say, oh, look at that. That's pretty cool. We will meet again in the next video for nitrogen nucleophiles.